Thank you. I would like to thank to the organizers of this conference for doing their job in such unusual times. It might be not so easy. And also thank you for inviting me here. Let me share my screen. Here is the title. Let me first say how this is related to the topics of this conference. So I'm going to speak about some p-adic phenomenon, p-adic property of period functions. Period functions are solutions to differential equations that come from algebraic geometry, so-called Picard-Fuchs or Gauss-Manin differential equations. And so by that reason, what I will speak about is related to arithmetic D-modules and p-adic local systems, I believe. And on the other hand, this talk is based on my joint work with Fritz Beukers, which is called Dwork crystals, and it will appear soon in the International Mathematical Research Notices. In that work, we do explicit Cartier operation on cohomology, DRAM cohomology of hypersurfaces, which has a classical description due to Griffiths and Butterev. So we do toric hypersurfaces, and the point of our work is that our Cartier operation is so explicit that it can be used to prove certain elementary facts or facts formulated in terms of combinatorics or number theory. So this talk is about applications of p-adic cohomology. So I will start with explaining what Dwork's congruences are. This is a phenomenon which I want to explain in this talk, and this is a particular application of our work with Fritz Beukers. So my setup is as follows. We have a Laurent polynomial in n variables with integral coefficients. The support is the set of exponent vectors in the monomials of this Laurent polynomial. So these are integral points in the n-dimensional space, and the Newton polytope of this Laurent polynomial G will be denoted by delta. Delta is the convex hull of the support. The main object of our interest is the sequence of integers, which we obtain as coefficients of x to the 0, so constant terms, in the sequence of powers of a fixed Laurent polynomial. For example, let's take this Laurent polynomial x1 plus x2 plus 1 over x1 over x2 in two variables. So the exponent vectors are 1, 0, 0, 1, and minus 1, minus 1. You can see them on this picture. The bold point is the origin. The convex hull is drawn here. This is the Newton polytope delta. And then if we raise g to some power to get the constant term, we need to take each monomial the same number of times. Therefore, there will be constant terms only when k is divisible by 3. And there is a simple binomial formula for the sequence in this case. This sequence is interesting only when 0 is inside of the Newton polytope. Otherwise, this will be just some sequence of zeros. And well, we could take any other point inside of the Newton polytope and then consider, say, point. We will consider some point u instead of 0, and then we will take coefficient of x to the ku in g of x to the k. That's an equivalent thing. So restricting ourselves to the origin is doesn't actually reduce our generality. So we will speak about p-adic properties of such sequences, and you can see that many sequences can be generated this way. Our example is pretty simple. There are many other examples. The phenomenon I want to consider, Dwork's congruences, can be formulated in terms of the generating function of this sequence. So CKs are our constant terms of powers of a fixed Laurent polynomial. We introduce another variable t and consider the generating series. This is a formal series with integral coefficients. And we will also need truncations. Gamma m means the truncation of the first m terms in gamma. So everything up to degree t to the m. Here is the statement, which I call Dwork's congruences. So assume that 0, the origin, is the only internal integral point in the Newton polytope of G. In this case, for any prime p and any integer s, we have the following congruence modulo p to the s for the ratio of gamma of t over gamma of t to the p and the ratio of two truncations. So this congruence can be, to see in concrete terms what it means, we observe that C0 is 1. So these are formal series which start with 1, and by this reason 1 over gamma is also a power series with integral coefficients. So what we see here in the left-hand side is a formal series with integral coefficients. The same is true for the right-hand side. So the congruence says that coefficients at each power of t are congruent modulo p to the s. Looking at this more closely, we see that this theorem gives a p-adic approximation of this ratio by rational functions. So it basically states that this ratio is a p-adic analytic element or rigid analytic function in the same sense of Krasner. So we want to explain this phenomenon. We want to give a construction, a homological construction of this p-adic analytic function, and then to explain precisely where such a congruence with truncations could come from. We call it Dwork's congruence because it was observed by Bernard Dwork in his work on rationality of zeta functions and deformation theory of zeta functions for families of algebraic varieties, families of hypersurfaces. But Dwork proved it only in certain cases where gamma is a particular hypergeometric function. So back in 2013, we found this generalization, which has very little assumptions, only this one, that 0 is the only internal integral point in the Newton polytope. So it applies to many sequences of constant terms of powers. And together with Anton Mellit, we gave a combinatorial proof of this theorem. But that proof was not really satisfactory. It didn't explain the appearance of the p-adic analytic element in this theorem. And since then, I was looking for more conceptual explanations. And in my recent work with Fritz Beukers, we were able to give such an explanation. So the goal of this talk is to explain this congruence cohomologically. I will prove this theorem, basically. On the combinatorial side, let me just make this remark so that you could maybe remember what Dwork's congruences are, because when we look at the modulo p, so just plug s equals 1 here, that gives a very particular property of the sequence of constant terms of powers, namely, so modulo p is p to the s minus 1 is 0, so what stands here is just 1. And then when we multiply out, we get that modulo p, the generating function, is congruent to its first truncation times the function to t to the p. And we can continue with gamma t to the p and so on. So there will be this infinite product on this side. And when we see what it does to coefficients, so every index k can be written to the base p with the digits k0, k1, k2 between 0 and p-1, then our congruence says that ck is congruent to the product of ck0, ck1 up to ckm modulo p. So the whole sequence is determined by the first p terms by this particular law, which is usually called Lucas congruence, because in the literature one can find many particular examples of such congruences. Lucas' theorem was done for binomial coefficients initially. And in general, for general S, this congruence says that the whole sequence is determined modulo p to the s by the first p to the s terms in the sequence. But that was sort of a side remark for us. Let's move towards the proof. So I will start with the observation about the meaning of this generating function. So we can write it as the following integral. To see that this equality is true, we can expand 1 over 1 minus tg as a geometric series and sum t to the k, g to the k. And then the integration here is over the product of circles around the origin on each coordinate. So Cauchy formula gives us that for t to the kg of x to the k, we obtain this term c to the k, t to the k here. This formula here tells us that our generating function actually has some analytic properties. For example, in C topology, it's convergent in some neighborhood of the origin. But what's important to us, it's a period integral. Namely, we have an algebraic variety here, which is the complement of the hypersurface of zeros of this polynomial in the denominator. Its complement in the n-dimensional torus. Let me call this algebraic variety X. Here we see a regular n form on this complement of the hypersurface. Integration, it factors through Dirac cohomology, meaning that it vanishes on exact forms by Stokes' theorem. So we could actually, this function gamma depends on the class of this form in Dirac cohomology. And in particular, from this, we see that our function gamma satisfies an ordinary differential equation in the case when this Dirac cohomology is finite. But actually, later we'll be able to work with the case when this module is of infinite rank. You will see that we really don't want any geometric assumptions. We want to prove a theorem which doesn't assume any smoothness of the hypersurface. So from this slide, just remember that this gamma of t has a presentation as an integral, and such integrals of algebraic differential forms over topological cycles, they are called period integrals. When t is fixed, the value of such an integral is called a period, and this notion was introduced by Grothendieck. And when we think of t as being a parameter, we say that we have families of periods or period functions, and they satisfy linear differential equations, which are called Picard-Fuchs differential equations or Gauss-Manin differential equations. So now let's speak in general about Dirac cohomology of toric hypersurfaces. So let F be a Laurent polynomial with coefficients in a ring R, which is a characteristic zero domain. For our applications, we will be interested in something like the ring of polynomials Z of t. So one can think it's Z or Z of t, for example. Let XF be the respective toric hypersurface. Delta be the Newton polytope of this Laurent polynomial. And well, we want to describe the Dirac cohomology of the complement, and the recipe was given by Griffiths and Buttery. Let me show you how this can be done. We consider the R module, R is this ring of differential n forms on the complement of the hypersurface. They look like, so there is always this term dx1 over x1 dxn over xn times a rational function. But we restrict to rational functions where the support of the numerator is in m times delta. That's a trick because to compute Dirac cohomology, there is no such condition. One should take all regular functions on the complement, but this trick will work for us, for our purposes. So in a similar way, one can define n-1 differential forms with the same restriction on supports. And these are two R modules. There are these factorials standing here. This is because we want to get congruences in the end. So when R is a field, for example, then the factorials do not matter. So really Griffiths and Buttery consider the case of fields, but we will need them in our theorems. So that just think that it's a trick. Classically, we have this relation that when we quotient this R module by this R module, we obtain the Dirac cohomology of the complement of the hypersurface of zeros under certain conditions. So these conditions are called that F is delta regular, and for this theorem, we possibly have to localize the ring R. So when we started with Z of t, we would have to localize it. I will show you how this is done in examples. And this quotient is, when our conditions are satisfied, it's a free module of the same rank, which depends on the volume of the Newton polytope delta. Actually, I'm not saying what this condition is. It includes smoothness. So in particular, the hypersurface would be smooth to have this finite dimensional Dirac cohomology. And I'm not given the condition because I'm going to avoid it. So what is written down here is a side remark, basically. We will not use this delta regularity later. Instead, we will work with this module on the left. And we will do all our constructions here. And just remember that under some conditions, this is Dirac cohomology. Under some conditions, it's of finite rank, but it can be of infinite rank, this quotient. Here is an example. This will be our running example, this Laurent polynomial here. In this case, the volume of delta is 3/2, and after we localize the ring of polynomials by the inverse of this polynomial, the quotient will be of a free module of rank 5. This is Dirac cohomology of the hypersurface. But let me tell you where we are heading to prove our theorem. We want to cut out a smaller piece, a subquotient in the Dirac cohomology, and to construct an operation, the Cartier operation, which will preserve this piece. And the matrix of this Cartier operation will be our p-adic analytic element in the theorem, gamma of t divided by gamma of t to the p. So I will proceed with cutting Dirac cohomology into pieces. The first way to cut out smaller modules is by support. So when mu is a subset of delta, we can restrict our differential n forms by adding this restriction that support of every rational function here, support of the numerator is in m times mu instead of m times delta. So it's a submodule of omega n f, the submodule of differential n forms on the complement. And this has some meaning in the theory of Dirac cohomology only when mu is open in the following finite topology. So a subset of the Newton polytope is called open when delta minus mu is a union of faces, maybe of varying dimensions, of any dimensions. Here are examples of open sets. This is the interior of delta, but we can also glue interiors of some edges and so on. By setting properly sets mu, we can describe the weight filtration on the RAM cohomology using this idea of restricting the support of differential forms. And in the above example, if we restrict to the interior of delta, we will get a two-dimensional R module instead of five-dimensional R module. But still we want something of rank 1, which will be responsible for the phenomenon in our theorem, for Dwork's congruences. So let me proceed and explain which tools are needed for this. So we will be doing formal expansions of rational functions. This is a very simple thing. Let me explain it. So if f is our Laurent polynomial, we fix a vertex of the Newton polytope, call it B, and we will be doing formal expansions at B. That's the name of the operation, and the operation proceeds as follows. So in the rational function with the power of f in the denominator, in this f, we take out the monomial corresponding to the vertex B. So f b x to the b, we take it out of the bracket. So inside, what's inside this L is the rest divided by this monomial. And then we just expand it using the binomial theorem, basically, but the power is minus m here. We write it as an infinite series. And when we look closely at the supports here, we will find out that the result will be an infinite series, which is supported in the following set. So we take the Newton polytope and move it. We subtract b. We move b to the origin, and then we consider the cone spanned by this shifted Newton polytope. That's where the sum here is supported. It's an infinite sum, but to every monomial only finitely many terms contribute. It's a well-defined operation, and it can be done for every vertex of the Newton polytope. Here are some quick examples. So if f is this, and we expanded the vertex corresponding to this monomial, what we do just means that we take this monomial out of the bracket in 1 over f, and then expand this as a geometric series, and that's what we get. But we could use a different vertex, and here the vertex is the monomial x2, and the result is a totally different infinite series. So for our purposes, we will fix some vertex and work with formal expansions as at a vertex. This allows us to define an operation on rational functions and consequently on differential forms. We call it a Cartier operation. And the idea also goes back to Dwork. So we fix a prime number. That's the first time that we fix the prime when we work with the RAM cohomology. And what we do, we take this formal series expansion, which was just explained, and remove the terms where the exponent vectors are not divisible by p, and then substitute to x to 1 over p, basically. So that's what our operation does on power series. It looks weird. It doesn't look like anything geometric at this point. And of course, it destroys the property of being a rational function. So when we start with an expansion of a rational function, we lose this property here, because we did something weird to the power series. But this can be, we will remedy this problem now by introducing Froubenius lifts. So suppose we have a Froubenius lift on our ring. A Froubenius lift is a ring endomorphism such that sigma of r minus r to the p is divisible by p for all elements R in our ring. For example, when R is Z, then the identity can work as a Froubenius lift due to Little-Fermat's theorem, on the ring of polynomials, the substitution of t into t to the p works as a Froubenius lift, but there are other Froubenius lifts which can be used. So suppose we have a fixed Froubenius lift on our ring R. In this case, we have the following property that when one takes a rational function with a power of f in the denominator, then this series which comes as a result of applying our Cartier operation can be approximated p-adically by rational functions with powers of f sigma in the denominator. F sigma is when we apply sigma to the coefficients of f. We change them by this Froubenius lift sigma. That's basically an elementary lemma, so that we can build a sequence of rational functions that approximate this series here. But when we want to approximate modulo p to the s, the degree of the numerator will grow infinitely usually. So when we consider this Cartier operation, it naturally leads us to the p-adic completion of the R module, which is the Dirac cohomology, or this quotient of closed n-forms by exact n-forms. So let me list some properties of this Cartier operation. So the first property is what I just said, this lemma, that the result of application of the Cartier operation lands in the p-adic completion of the module of n-forms for f sigma. Another interesting property is that this operation on p-adic completions, we can extend it to p-adic completions by linearity. It's independent of the choice of the vertex at which we are doing formal expansions. That's a nice lemma to prove, but other constructions of the same operation are possible, and they can be done independently of the vertex, not using formal expansions actually. Next, this Cartier operation maps exact forms into exact forms, so it actually it descends to the quotient by exact forms, which is like Dirac cohomology. And the reason is just from this formula, one can see the following commutation relation, p commutation relation. It doesn't commute with partial derivatives, but there is this multiplication by p. Then if our ring is ZP, for example, in this case, powers of the Cartier operation, actually traces of powers are well defined, and they count points on the complement of the hypersurface over the extensions of the field FP. And another property is that when mu is open set in our finite topology, so the complement of mu is a union of faces, in this case, the Cartier operation maps differential forms supported in mu to differential forms supported in mu. Okay, so let me now use these properties and state the key theorem of our work with Fritz-Beukers, which I'm going to apply to prove Dwork's congruences later. So for a subset mu in the Newton polytope, we denote by mu z the set of integral points in mu. There are some pictures here of these sets. We define the Hasse-Witt matrix corresponding to the set mu. It's called beta p mu here. That's an h by h matrix where h is the number of integral points in mu. And the entries of this matrix are in the ring R. The entries are coefficients of certain monomials in the p minus first power of the Laurent polynomial f. Under certain assumptions, so namely that the ring R is p-adically complete, mu is open in our finite topology, and the Hasse-Witt matrix is invertible in R, we have the following: that the quotient of the module of differential n-forms, well, it's p-adic completion, by so-called formally exact forms. I will explain what this is in a moment. Is a free R module of rank H, where H is the point count here. Is a free R module of rank H spanned by the differential forms which correspond to this internal integral points in mu, not internal, but integral points in the set mu. Okay, so formally exact forms here are differential n forms which can be written as, which can be integrated, but not integrated as rational forms, but as formal forms, so as formal series. Remember that we are doing formal expansions. So we do the formal expansion of our form, and then there will be some n-1 power, n-1 form with coefficients are power series supported in our cone, such that this form is a differential of that one. In particular, that module here is it includes exact forms. So what is written here is a quotient of Dirac cohomology, but we did this p-adic completion. So basically this is the quotient of the p-adic completion of the module omega n divided by d omega n-1, p-adic completion of Dirac cohomology. And this quotient appears to be free under the condition which doesn't, this invertibility of the Hasse-Witt matrix, which does not involve smoothness of the hypersurface, for example. So it's a finiteness theorem without assuming smoothness. And usually the conditions in this theorem can be achieved by extending the ring R. For example, when we start with R being the ring of polynomials in the variable t, and then to have it p-adically complete, we would do the p-adic completion of this ring. But to make beta p of mu invertible, what we do is we can consider its determinant. If its determinant is not divisible by p, then we just invert this polynomial in our ring. So we localize the ring and then do the p-adic completion. That's how it works. So usually the conditions here are not hard to achieve by extending the ring R. Okay. Now, let me show you how this theorem can be applied to prove Dwork's congruences. So from now on, we will work back in our setting from the very beginning. G is a Laurent polynomial with coefficients in Z. 0 is the only internal integral point in the Newton polytope. So the interior of delta contains no other lattice points. Gamma of t is the generating series of the sequence ck, where ck is the constant term of the k's power of g. To apply our theorem, we take f to be 1 minus tg, where t is our new variable. We take the set mu to be the interior of the Newton polytope. Our condition here about a unique integral internal point means that mu z is just the origin here. So the Hasse-Witt matrix in the theorem will be a 1-by-1 matrix because there is only one point. And this matrix is the constant term of the p minus first power of f. So it's a polynomial of degree at most p minus 1 here. To achieve the conditions of the theorem, let's take the localization of the ring of polynomials by this Hasse-Witt polynomial, and let's take the p-adic completion. Now the theorem should be applicable. Its conditions are satisfied. We take a particular Froubenius Lift, which sends t to the p on this ring R. So by our theorem, here is the differential form which spans the quotient in the theorem of all n forms by so-called formally exact forms. And that quotient is of rank 1 spanned by this form. So when we apply the Cartier operation to this form, it should be the same form for F sigma. So F sigma means we substitute T to the P now. Some element of R, this is the matrix of the Cartier operation on the finite rank quotient. So it's a 1-by-1 thing. It's an element of R plus a formally exact form. That's the output of the theorem, basically. And from this, we want to derive congruences. The first thing to do is to integrate this equality. So we will apply our integration, the residue map, which sends differential n forms to, so we integrate over the product of circles on each coordinate as before. And we will call it the residue map, residue at 0. This is an R-linear map which vanishes on exact forms and also on formally exact forms. And it's invariant under the Cartier operation. It's a little lemma to prove this invariance, but it's not very hard. So this is what we get from the theorem, that there exists such a lambda, that we have such an equality. Now let's apply the residue map. So the residue at 0 is, well, we do the same trick, this geometric series expansion for these differential forms, then integrate, and we get our generating function of constant terms of powers here. This is on this side because the map is Cartier invariant, that CP here will not change anything, so we obtain gamma of T here. Now, on formally exact forms, the residue vanishes, and on this form, we just do the same computation with T substituted by T to the P. So what we get by integrating this equality, we get it that our element lambda is the ratio of gamma of T or gamma of T to the P. This is the main player in the theorem. It appears to be the Cartier matrix on certain rank 1 subquotient in de Rham cohomology. And it could be that the de Rham cohomology itself is of infinite rank, but this subquotient is of finite rank because our conditions are satisfied. Also, we achieved something already. We didn't prove congruences yet, but if you remember what the ring R is a p-adic completion of a localization of the ring of polynomials by this Hasse-Witt polynomial here. So at this point, we already know that lambda is a p-adic analytic element, a rigid analytic function. It can be approximated by rational functions with the powers of this Hasse-Witt polynomial in the denominator. But we wanted to prove some particular approximation given by Dwork's congruences. So how would we do that? A new idea is needed here. We don't know yet. But in fact, to prove these congruences, we are going to do the same trick as on the previous slide, where we computed lambda, but to modify the residue map. So instead of the residue map here, we will do something else. A residue map is an example of a period map, a map on differential forms which vanishes on exact forms. And now we introduce a tool which modifies period maps in the following way. So we will fix any Laurent polynomial called H, and then our maps will be and fix an integer m. So we will send a differential form to the residue of this differential form multiplied by the m's power of H. What does this map do? Firstly, we destroyed the property of being 0 on exact forms, because when omega is exact, then some polynomial times omega is not necessarily exact. But apparently this property is preserved modulo m by an elementary reason. So suppose you apply this map to some d eta, to an exact form, then h to the m d eta is the same as d h to the m eta modulo m. By this reason, if you consider this map modulo m, it still vanishes on exact forms. So we call such things period maps modulo m. Another property is, again, some invariance under the Cartier operation, which is not hard to show. And now for our application for Dwork's congruences, we do the following. So this is our polynomial f, which we are working with. So we consider these are our period maps. So we will take a linear combination of the period maps where h are two different Laurent polynomials. In the first case, it's 1, so it's the residue map that we had before. But then we take t times g, and this looks scary at first glance. This is a formula, but in fact, what this formula does, it computes the residue at 0 of something, which appears to be a polynomial in T, and in fact, it's the truncation of our generating series of constant terms of powers. So what we gain here is the understanding that truncations are periods modulo M. They are like period maps applied to differential forms, but we are considering some arithmetic period maps. Usually period maps take transcendental values. When we integrate rational differential forms against topological cycles, we are getting some transcendental numbers or transcendental functions. But in this case, we work with maps which land in rational functions, or which land in some nice modules and which can be considered modulo M. And truncations appear to be such periods. So using this observation that truncations are periods, we just applied period maps of this kind, period maps written here, and do the same algebra as on the slide where we computed the Cartier matrix on this rank 1 subquotient correspondent to the interior of the Newton polytope in our example. And the result is that lambda, the ratio, well, the Cartier matrix, or the ratio of gamma of t over gamma of t to the p, we obtain that it's congruent to some ratio of truncations modulo p to the power of p that divides m. And this is true for any integer m. This is Dwork's congruence. So this is what we wanted to achieve, actually. So our theorem is proved. Thank you for your attention.